again, theta is v over c. That's the speed of this charged particle q moving in that direction with velocity v according to the lab frame, right? So O is the lab frame. And in this case here, I guess it's kind of misleading. The way I should draw it is that I made a mistake. It's always easy to confuse prime and unprime frame. This is in the O frame, okay? In the O frame, I have a charge q moving with velocity v, right? And O prime is the lab. Okay. Things are always simple in the stationary frame of a charged particle, and it's not so simple, right? O prime is the lab frame, and we just happen to have plus q moving in that direction, right? So at that point in time, O and O prime coincide. Okay. And if you look at this is part of the confusion. Some people ask a question on Wednesday, is that I was drawing an elongated shape like this. This is a polar diagram of the magnitude. Okay, so in any direction theta prime, right, in the lab frame, this is the magnitude of the electric field. And this thing is moving with some velocity v. This pancake is moving to the right with some velocity v. Okay?
So in the frame of the particle that's moving, does it see its field as being normal?
Yes, yes. In the rest frame of the particle,
yeah.
Then the field is just regularly out. E is q over 4 pi epsilon naught. It's radial and it's central. Okay? But in the lab frame, you see this thing moving at some velocity v, and it gets squeezed. The faster you go, the more you squeeze it. Okay? Let's take that off the slide. Okay? And also, this is, I know in relativity you have to be careful about time, right? But here in this case, after all said and done in the analysis, this is actually instantaneous. Meaning, say, at time equal to 0, t prime equal to 0, this particle happened to be at the origin of my reference frame, right? And it has an instantaneous velocity v at that particular time here, and the field is just given by this formula. Right? This is at time t or t prime equal to 0. Okay? And if you worry that maybe there is information is moving at faster than the speed of light in this case, that's not the case here. What happened is this particle is moving at some velocity for a long time. Right? So the solution is a solution for a constant velocity particle moving in a frame, right? And then this calculation will give you the field at that particular time when the particle is at some position, r. Is this confusing or is clear? Okay. So if you look at it in time or in space, right? I guess this is an O prime. Right? O prime is a lab here. You get something that looks like this, and it's moving in that direction. Okay. And if I put a charged particle Q, right, at that particular time t, then the force on that charge is just Q times d1, wherever the charge is. Okay. these charges have interpretation R prime, theta prime. You calculate upon theta prime, and you calculate the electric field, and then you can calculate the force. Okay. So, by principle of superposition, another example. If I have many of these, of charge Q moving at some velocity v, I get it like this. If I have many of them, then as usual the field adds, right? So I can construct, say, a sheet, okay, of charge density sigma moving in that direction with some velocity v, right? And if you sum all this field, you'll see that the field here is normal. And we derived this, right? Remember from our discussion on Wednesday that if we have a parallel plate, sigma minus sigma, right? And this thing is you push this at some velocity v, right? Then we actually derive that the field in the lab frame is normal. It's not quite clear why that has to be the case, right? Because you already break the symmetry, right? Because there is a direction of motion in this case. And there's nothing that says that the field cannot be pointed in that direction. Say, or in that direction. Right? This is the proof. Right? Because what happened here is that for each individual charge, point charge, the field is still symmetrical around this point, right? So when you add all of the charges to form a sheet, everything is still pointing in that direction, right? All the field that's pointing in the plus minus x direction will cancel. Okay? Same thing, right? If I have, we'll do this, maybe we'll do this, I'm not sure if I have time, but maybe we'll do this on Monday. If I have a line charge, lambda, right, and it's moving at some velocity in this direction, right? And also because lambda is constructed by, you know, superposition of individual charges, right? Then the field here, you know, it also is very
So this is the things that we did earlier, where we just said that it was like infinitely spread, and like where is it pointing? This
yes, I mean, we assume
that
in our discussion of parallel plates,
yeah.
We look at this carefully. We haven't looked at this yet.
Right, yeah.
We look at this, and we in our calculation of the Gauss law, we assume that the field, you know, in the lab frame is normal. But where does it come from? You already break the symmetry, right? So maybe it's not normal.
Yeah.
But this actually shows that it has to be normal.
Because each individual has a thing going on.
Yes, it all looks like this, right?
Mm-hmm. Wait, but why do we assume it's moving in the?
This is the field when it's moving.
But I mean, inside the parallel plate, like they wouldn't be moving, right?
Yes, in this case here, right? I have a sheet of charge.
Yeah.
Right, and it's boosted in that direction, right? So it's moving to the right.
Mm-hmm.
And then we actually did the calculation. I don't know if you remember, the calculation is that E prime is in the lab frame, right? Is equal to gamma.
Oh, right.
Right.
Mm-hmm. It's
boosted so that the field is actually larger, but it's still normal.
Mm-hmm.
Right? And the explanation for the fact it's normal comes from this. Right? Because you can still construct the charge density out of individual charges.
So this parallel plate is from the perspective of the stationary.
Yes.
Okay.
This is so there's this is all this analysis is from the point of view of a guy who's in the lab, John. Right. Okay. Question? So let's see. Let's summarize. So far, in the first three chapters, chapter 1 to 3, right, we're mostly talking about stationary charge, force on stationary charge due to also stationary charge, right? Charge. This is easy to do, right? Calculate the electric field anywhere at R. The force on that charge is just that. Okay? We spend the first 3 weeks on this, right, of electrostatic. And then, just this week, we look at force on stationary charge. Q, say, right? Due to moving charges. Okay. So, say in this case here, I have a parallel plate that's moving at some velocity v, right? And I want to look at the charge on the force on Q. Q is a dash charge that belongs to Charlie, right? Q is stationary. Right? And we found the force on Q is just Q times gamma E. Right? There's a gamma here because the plate is moving. Right? Similarly, in the case of a moving charge, same thing, right? Moving charge, you have a field that looks like this, right? And then you can calculate the force. Okay? But how about the other way around? That's the next one I want to look at, right? Case number 3 is when you have a force on moving charges. On moving charges. So I have suppose I have Q moving at some velocity v, right? Say, and then it's encounter a parallel plate. This parallel plate belongs to Charlie. So it's stationary. What's the force on this guy? Right? And another example would be, you can generalize this. Again, this is Q moving at some velocity v, but I also have a parallel plate that's moving at some velocity v prime. Right? And we want to calculate this velocity. There is a relative speed between these two, between the plate and the charge, right? And then you have another force, right? Or say in the case of this, right? If I have two of these pancakes, right? I have a proton, say in the Large Hadron Collider, a proton colliding with one another, right? Approaching one another. What's the force between the two? That's what we want to calculate next. But before we do that, also another situation would be, say if I have two protons, they're moving in the same direction, right? And one is above the other. What's the force on one due to the other? Right? How do you calculate that? You have to do like this, and here it's like this, and then they go. Right? That's what we want to calculate. But before we do that, we have to go back to relativity again. Remember, in all this discussion, things are easy when you analyze it in the rest frame of the particle. We always want to analyze things in the rest frame of the particle, and then we move back to the lab frame. Okay? So let's look at the velocity equation in special relativity. Any questions so far before I go back to relativity again? I wrote this ahead of time to cheat because there's a lot of algebra. I don't want to waste so much time writing it down. Any question on this? No question? Yeah. We know that, this is early on from last week when we talked about relativity, that Galilean velocity transformation is strong, right? So there is, if you shine a light inside a train and the train is moving, and from the point of view of somebody on the ground, the speed of the light, the speed of that flash light is still c, right? So we want to be able to actually calculate that within special relativity. So again, here you have two coordinate system O and O prime. O prime is moving at some velocity v to the right with respect to O, and the Lorentz transformation is given by this, right? X prime. Sometimes I would write something like this, right? Just to indicate this is what's happening. Okay, it's just a shorthand. And I want to look at two objects: a velocity of a particle according to O, and the velocity of a particle according to O prime. Right? How are they related with respect to one another? Okay, and then U is the velocity here. I'm sticking to the notation that Purcell has. Equals U for velocity, at least on chapter 5. And U is just dx dt, d by dt, dc dt, right? In the O frame and in the O prime frame. So to analyze this, let's consider a particle that's at time equal to 0 is at the origin O, right? And it's moving at some velocity, right? So at some time t later, the position in the x is given by ux times t, right? Okay. Ux prime then is equal to x prime divided by t prime, right? And then I substituted formula from Lorentz transformation here, okay? And I'll get the ux prime is given by this formula here, okay? Same thing here, uy prime is y prime divided by t prime, and then you get something like this, okay? And the formula for uc prime is the same as uy prime. Just substitute c for y. And then you can do the inverse. You can either do the algebra for the inverse, or for the inverse, right? The whole thing is symmetrical according to O prime, always moving to the left, right? Therefore, you just have to replace all the minus sign with plus. So ux is ux prime plus v divided by 1 plus ux prime v divided by c squared. Uy prime is still the same, except that it's also a plus here. And you can try to actually plot this function, and you realize that nothing will exceed the speed of light. Right? Think of that situation. That's just, since this is kind of complicated, let's just look at the situation right more carefully.
I have a question.
Yes.
When you say the inverse, are you just talking about the other frame?
Yes, according to the other frame. Right, yeah. So I have a relationship between u prime and u.
Okay.
Right? So if I know u, what is u prime? Right? And then the other way around. If I know u prime, what is u? Right? And then either you can just invert the equation, right? Which is a lot of algebra. Or you just know that, well, according to O prime, the whole thing is symmetrical, right? According to O prime, O is just moving to the left. So the velocity is negative, right? So if you look at the inverse case here, I don't think I make an algebraic mistake. I think this is correct. So if I have a train moving at some velocity v, this is O prime, and charge is here, O, right? And then this guy is going to ball at some velocity x prime, right? Then according to Charlie, ux is just ux prime plus v divided by 1 plus ux prime v over c squared, right? If you plot this, as a function of ux prime, you'll see that, suppose this is, I don't know, suppose p is 0.9 minus % of the lambda series. Then what happened here is that this was 0.9 and 0.9. So you have something that looks like this. But it will never reach 1c. Okay? Because of this formula here. I mean, you can just plot this formula on Mathematica or whatever function, whatever graphing calculator that you have. Question on this? No? Is this clear so far? What? I just want to give you time to write all this too, because I sort of cheated. I put it all beforehand. Yes, question?
Oh no, I was just wondering. You were standing in front of the x-axis.
Yes.
This is rest frame versus moving frame.
Yes, this is what is the velocity in the rest frame of the lab, right? And then the prime frame is the moving frame, right? So there's a prime frame that moves to the right with some velocity. You just have to be careful. I mean, we'll see later on. But we have to be careful about what's moving and what's not moving, because I'm not always consistent, and Purcell's not always consistent either. Any questions so far? Okay. So as you see, this formula is kind of complicated, right? In fact, if you take 7C next year, we'll solve a lot of problems like that has to do with velocity addition. But I just want to point out that it's complicated. They don't transform. They don't transform simply like a Lorentz transformation, right? U prime and U are not related by Lorentz transformation. Okay, it doesn't look like that, right? Remember Lorentz transformation, the formula looks like this, right? It looks very beautiful. Right? U is kind of ugly. Right? The formula for Lorentz transformation look a lot more symmetrical between x and t. Right? So, and also, if from the formula for Lorentz transformation, I talked about this a little bit in the discussion. This is concept of intervals, right? Which is for Euclidean geometry, it's just the distance. The distance is always independent of frames, right? But in special relativity, it's actually the concept of interval, which is given by s squared is equal to c t squared minus dx squared plus dy squared plus dc squared. Okay. And say in the prime frame, you have something like this. Prime squared plus dy, prime squared plus dc, prime squared, right? And ds squared is actually invariant. It's just like charge. It's invariant under Lorentz transformation. Right? So ds squared is equal to ds prime squared. It never changes. Okay. Can I give you something? This leads to development of a new concept called proper time. Proper time t tau is a time interval measured by a clock. Time interval. Measured by a clock moving with a particle. Suppose I have a particle moving at some velocity u, right? I can associate with that particle a clock, right? And suppose you have a time elapse tau from that clock, then you know from Lorentz transformation. Now let me actually backtrack a little bit. This tau is just equal to, because the clock is moving with the particle, right? Then if I look at this interval, or in this case the second one, right? Because it's the prime one, right? It's a prime frame, or prime frame, right? Then ds prime squared is just c squared t squared, right? Minus 0. Because the dx prime squared is 0, right? Because the clock is moving together, is moving with the coordinate system, right? See what I'm saying? So delta x prime is 0, delta y prime is 0, delta c prime is 0.
So does dx prime measure the difference in the change in distance?
In the prime frame, right? So suppose I put the particle in the clock. So whatever particle I'm studying here, say call it Q, right? I put the clock there, which is in the prime frame, moving at some velocity v, O prime, right? Then according to this frame, delta x is 0, delta x prime is 0, right? So what I have is ds prime is just c squared delta t squared,
Okay.
right? And then delta t prime squared is 0, right? But there is a special name for this delta t prime. It's called t tau. Right? So the ct tau is just 1 over c, yes. Right? And ds is always the same. This is invariant, right? ds is invariant, right? So t tau is always the same. T tau is also invariant. This is a special property of a clock that is attached to the particle. Okay? And there is a reason I want to do this. We're not doing much about further velocity addition because it's complicated. We'll do a lot more of that in 7C. But remember time dilation. According to you, according to Charlie, then delta t, which is gamma t tau. Right? Okay? So, or to write it again, t tau is just delta t over dt over gamma. Okay? So, let's see. With this concept of proper time, I'm going to construct an object, right? It's called P. It's called momentum, right? For momentum. But Px is given by, instead of usually in classical physics, in Newtonian physics, momentum is just what? Mass times u, right? Okay? But u is a very complicated object, right? Because u is just m dx dt, right? And the reason it's complicated because this x has a Lorentz contraction. and t is a time dilation. So I'm going to construct something else, and just bear with me for now, and there is a reason for it. That this is given by m dx tau. Okay. Now x transformed like a Lorentz transformation, but tau is invariant. Right? Okay. So this object might have more of a promise. Okay, as you will see. So since t tau is dt over gamma, then this is become gamma m. Right? That means that dx dt is gamma m. Okay, and similarly, y is gamma m y, and then pz equal to gamma m z. Okay, and we need one more object, right? The last one. The last one is going to be energy over c, right? And there is a reason for all this name, but for now, let's just think of it as a variable. Okay, and where was I? This E over c then is just mc. I want to construct something so that they can transform like a Lorentz transformation, right? Let me erase this since we don't like this, right? We don't like this velocity addition. So let me rewrite this equation, right? X prime is equal to gamma x minus beta ct, right? And then here t prime is equal to, let me write it as a ct prime is gamma ct minus beta x beta x, right? Okay. Okay. So let's see here. If I do this, just bear with me for now, I just remember the formula. If I construct an object called E over C, it's given by mc times dt tau. This is the x d tau, right? And this is the y d tau. This is m dz d tau, right? So this act like a Lorentz vector, right? So I want an object that looks like t, right? So I have mc dt d tau, right? And d tau is invariant. So this becomes gamma m c. Okay. So let's erase this for now. Let's erase this. And let's look at the last formula. The last formula should remind you of something. E is equal to gamma m mc squared, right? This is the famous formula that's on all T-shape, right? When you have m, or let's call this m0, say, so the mass of the particle, where m is gamma and not c squared and c naught, right? This is what you're familiar with. Right? So when I have object like this, then the transformation is given by dx prime equal to gamma dx minus beta d over c, right? And d over c will be prime, but is equal to gamma d over c minus beta dx. And the usual thing, dy prime is equal to dy, and dc prime is equal to dc. Okay? Right? And this is just the Lorentz transformation, right? I know P and E, right? I have a Lorentz transformation into P prime, E prime. very simple, right? If you remember Lorentz transformation, you remember our momentum transform. This is called form momentum. This is a fancy name, just to differentiate it from classical momentum. Okay? And just like you have this invariant, ds squared, right? Same thing here, you have a form momentum invariant. In this case, if you remember, if you look at this, play the role of time, this play the role of x, right? Okay? Then if you look at the, where is the formula for the invariant? If you recall, ds squared is just c d squared minus dx squared plus dy squared plus dc squared. Right? These are all vectors, right? And this is vectors, and the e is a scalar. Then it's the same thing here. I have just to copy that. I have this is the part I always forget about the c, right? E over c squared plus minus dx squared plus dy squared plus dc squared. This is also invariant. Okay. So this is also equal to e prime over c squared minus dx prime squared plus y prime squared plus c prime squared. Okay. And there is the invariant is equal to m naught squared c squared. Okay, so then you have again this is the formula that I believe you see this, right? E squared is equal to c squared e squared plus m naught squared c4. This formula is the same as that formula. Okay? And so far in electrostatic, I haven't cheated yet, right? I haven't pulled anything out of, what is the phrase usually? I haven't pulled anything out of my head. Everything I derived. Unlike in thermodynamics, I pull things out of my head. Equipartition theorem, say, right? The Boltzmann distribution, right? That was pulled out of my head. Here, so far I haven't done anything that I pull out of my head except I will do that next week. So it turns out in special relativity, conservation, I'm not going to derive this of momentum, and you can look at relativity tags on this. When I talk about conservation of momentum, it's the form momentum that is conserved. It's not the classical momentum. Okay. So when I do conservation of momentum for a collation of a particle, or a reduced particle, right, it's actually this momentum that you have to worry about. And this energy. Okay. Of course, in the limit of small velocity, then you back into the whole 7A conservation of a mechanical momentum and energy. Okay. But relativistically, the thing that's conserved is this object here. It's the form momentum object.
Why do we call it 4 momentum? Is that a thing?
I don't know why it's called
Just,
4.
okay.
I think it's just to distinguish it from the because there are 4 objects here that they're somehow on equal footing, right? Px, Py, Pc, and then this object. Right? Just to distinguish it from 3 momentum. in Newtonian physics, the momentum is just px equal to m dx dy dc, right? And this is a different object. And the same thing you will learn in 7c. I don't know if you learn in 7c or not. There is a three velocity, which is the regular velocity that transforms in an ugly way that I erased, right? But you can also talk about fourth velocity, right? The fourth velocity is just dx and tau, right? Instead of t, you use tau.
Because it's tau.
Tau is invariant, right? T is not. And the fact that tau is invariant makes sure that the only thing that transforms is the dx part.
So are you saying that like px, py, pz are like the normal momenta,
Yes.
and then the px prime, e prime over c, py prime, pz prime are the components of the four momenta?
No. They are all for momentum. This is all for momentum. The expression p, be careful, p, say px is not mux. Right? This is wrong. This is actually equal to gamma mux. There's a gamma in it. Of course, when velocity is small, gamma is equal to gamma is equal to 1. Right? When v is, this is the velocity of the frame, is close to 0, then gamma is close to 1. Right? Then you're back in the old classical Newtonian case. Right? Mass, momentum is just mass times velocity. But relativistically, it's not. Relativistically, momentum is given by gamma m times velocity.
So like what you wrote there is just like how to transform the four momentum, but the actual four momentum is all you have to do is just put gamma in front of.
Yes, gamma in front of, just formalistically, just put gamma in front of everything. Okay.
Where do you get E over C to MC dt?
Well, here I just want to create an object that transforms like a Lorentz transformation. Right? So I already have dx. So I just need dt here.
Why MC?
Oh, just dimensional, to make it dimensionally correct. There is a reason, but I'm running out of time. And this is not the reason what I want to talk about. What you have is conservation of form momentum. Right? And I was hoping to finish with the force in the prime frame is equal to force. Maybe you should just read this in the book. Oh, damn it. And then F prime in the perpendicular direction is 1/10 F prime. This is what we need. This is the formula that in the end what we need.
What is that?
And this force, or just to be more specific, dp prime dt prime is equal to, this is in the parallel direction, is equal to dp dt, and then dt perpendicular prime dt prime is equal to 1 over gamma dt perpendicular. So the dp transform simply like Lorentz transformation. Right, but the t transform with the time dilation, right? So when you do that, this is what you get: the relationship between force in one frame to force in another frame, and this is what we need to calculate. If I want to calculate the force on a proton that's moving with respect to another proton, right? I calculate it in the rest frame, where things are easy, where your old knowledge of chapter 1 to chapter 3 work, right? And I jump into the Charlie's frame, and I see this thing moving, right? And then the force just transforms like that. Right? And this just comes from that formula, from the form momentum formula.
So forces are not invariant?
Forces are not invariant. Yeah. You can also create concepts like force. Right? We talk about invariant. We talk about forces that transform like Lorentz transformation. We can talk about force velocity. This is for momentum, right? You can talk about force velocity. You can talk about force. But at the end of the day, what you want is still the force in the frame of interest. Right? So at the end of the day, you still have to do this. Okay? Because this is what Charlie will observe in his lab. Question? So on Monday, okay, Monday is the last day of chapter 5, otherwise I'm going to run behind. Monday I will talk about forces between two protons, heads-on and then in parallel, right? And then you have to read the rest of the chapter yourself on the forces from the wire. Or if I have time, I'll do that too. Any question on this? 2 minutes. Is this clear? This is complicated. This will take a long time to absorb, right? Relativity is always non-intuitive. The best thing is to sleep over it. Right? So meaning that you'll probably get it when you're doing one thing, right? But don't worry, you know, life is long. You'll get it next year.